Alright, welcome to mini lesson 6. It's the end of the week, at least according to my schedule. I hope everyone's had a good week. I hope you're going to do something a little bit fun on the weekend, maybe a little bit different. Don't go out of the house. There's no other thing to say. Just stay in your home. But let's do some physics, which is easy to do while sitting down. So we're going to talk about partition functions for internal degrees of freedom, and specifically in this lesson we'll focus on the example of rotational levels. This is the rotational level part is coming mostly from section 6.2 of Schroeder, pages 234 to 6. So here we go. We want to think about internal degrees of freedom, and if you think back to chapter 2 when we were doing multiplicities, we kind of marveled at how difficult it would be to include those inside a phase space picture, especially if you were to consider angular momentum where you have r cross p. You've sort of now mixed up the positions and the momenta of the particles, so they're no longer in sort of orthogonal coordinate axes. Makes it really hard. However, if we're working with partition function methods, it becomes pretty easy. So what we can imagine is that the total energy of some particle, let's just sort of imagine it as an ideal gas particle, where we've got translation of the center of mass of the particle, the molecule if you want, rotational energies of the molecule, and vibrational energies of the molecule. And so if we take all these different energy levels that appear inside this expression, couple them to a thermal reservoir. That's actually important to remember, that we always have to have a thermal reservoir conceptually for this picture of the partition function to be valid. Then we have a total partition function that ends up being the product of the partition function for the translations, the rotations, and the vibrations. So let's prove this. The total partition function is the sum over all of the possible quantum numbers of the Boltzmann factor, where these quantum numbers somehow appear inside the expression for total energy. And so we'll break that down into a sum over the translational quantum numbers. So those would be like the n sub x, n sub y, n sub z quantum numbers for the particle in a box. The rotational quantum numbers, so angular momentum type quantum numbers. And the vibrational quantum numbers, which will basically be simple harmonic oscillator indices. And so then the Boltzmann factors are e to the minus beta times this sum of e translation plus rotation plus vibration. And so the fact that the energy can be written as a sum means the Boltzmann factor can be broken down into a product of 3 separate Boltzmann factors. So we sum on all the quantum numbers of e to the minus beta translation, beta rotation, beta e vibration. And that makes it easy because now we've just separated everything out, and the total partition function is just the partition function for the translations times the partition function for the rotations times the partition function for the vibrations, just like we wanted. And so this is a really easy tool to use to include internal degrees of freedom in your statistical mechanics picture. A lot easier than having to use, say, some complex geometry in phase space. So let's just keep in mind that if we have n indistinguishable gas particles with internal degrees of freedom in each one, we can write the composite z as this total single particle partition function raised to the nth power over n factorial. And from there we've got thermodynamics by just taking F equals minus kBt natural log of z. And so a product that appears inside this z sub n can be broken out into a sum due to the logarithm. And so you're going to get basically a sum of contributions from each of the internal degrees of freedom contributing to the total free energy of the system. And so Schroeder carries along the internal free energy contributions inside of his analysis of the free energy of the ideal gas. So he doesn't specialize to a monatomic ideal gas necessarily when he does it, like we did in our last lecture. I think it was the last lecture. I've kind of lost track. So let's see. So let's move on and do an example. Excuse me. So I'd like to consider a diatomic molecule made of two different atoms. It's actually important that they're different. And please read Schroeder to understand why that's important. Again, section 6.2, when we talk about the rotations, that just has to do with the fact that if the atoms are different A and B, that means they're automatically distinguishable. If they're the same, you have to worry a little bit about the high symmetry making certain configurations equivalent. But the standard example of this kind of molecule is hydrogen chloride, or hydrochloric acid if you want. So if you go, oh, what am I doing here? What happened to my picture? All right, I lost my picture. It'll be in the next slide, whatever. So what we can do for this molecule is actually solve the time-independent Schrodinger equation to get the rotational energy levels. We can solve for the electronic orbitals of the molecule by doing a linear combination of atomic orbitals. So the hydrogen and the chlorine are bonded together by sort of mixing their hydrogen 1s orbital and the chlorine 3p orbital. You may have seen some of that in your modern physics class. And so this is the form of the rotational levels, where J is the rotational quantum number, and it can be any integer from 0 up to infinity. I is the moment of inertia, and we're going to just substitute h squared over 2I as little epsilon in this expression. So I just want to draw this picture because this is kind of the general idea behind molecular degrees of freedom. You've got the electronic energy as this blue curve that has a deep potential well. And so the x-axis here is the distance between the hydrogen and the chlorine atoms in the molecule. And so when they're very far apart, they're just isolated atoms. But as you bring them closer and closer together, they start to lower their energy by sharing electrons inside molecular orbitals. And there's some special distance, the equilibrium bond length, where they have a minimum in energy. And so inside this potential, the electrons basically see this kind of almost parabolic potential. And schematically, I'm showing you the internal energy levels that are associated with this molecular potential. And so the vibrational levels are the red lines, and they're an equally spaced set of harmonic oscillator solutions to the Schrodinger equation. So the energy spacing is given by h bar omega naught, and then which level you're in is determined by the quantum number. And we're going to talk about this in detail in the next mini lesson. For today, I want to focus on even lower energy quantum states, the E sub j, that are the rotational levels. So this says what are the quantum states of rotation of this diatomic molecule. And so the answer is they have an index j that can be any integer from 0 up to infinity. So j times j plus 1 times this energy scale epsilon, which is h squared over twice the moment of inertia of the molecule. So we're going to focus on these now. It's really important to focus on these because it actually brings up something associated with the partition function that we haven't had any reason to talk about yet, and that is degeneracy. So if you just try to sum over all the rotational levels and just plug in that formula for E of j, you're not going to get the right count of Boltzmann factors under this sum. And the reason is, if you pick a given value of j, you might have a degeneracy, which is more than one different state. In other words, more than one set of different quantum numbers that has the same energy, E of j. So make sure you understand all those words. In some of that, I guess I'm saying it kind of fast because there aren't that many words, but they're all important. So go back over this and make sure you see what I mean. So I'll try to explain it more here a little bit. Oops, I messed that up. Let's go back. So yeah, if we just simply sum the Boltzmann factors using the quantum numbers j, you'll not get the correct count. And so each j has 2j plus 1 different m sub j states that all have the same energy in zero magnetic field. So remember, if you have j equals 1, if you're doing atomic physics, you'd call that a p orbital. You can have m sub j equals -1, 0, or +1, and then in zero magnetic field, they all have the same energy, which is 2 times this little epsilon. So that's what it means to be degenerate. J equals 1 determines the energy, but in fact there are 3 truly different states that all have that energy. And you need to include a Boltzmann factor for each one of these. It's the same Boltzmann factor. It's e to the minus beta 2 epsilon. But they all have to be counted. They're not the same state. They're distinct. So we can include degeneracy inside of our partition function by writing it out as the sum on S of the degeneracy factor associated to the quantum level S times the Boltzmann factor, right? And so G of S, the degeneracy factor, tells us the number of degenerate states associated with each quantum number. For the case of rotations, we'll write it out this way, where we're summing on all the J angular momentum quantum numbers. G of J e to the minus beta EJ. And in this case, G of J is 2J plus 1, right? Because all the M sub J values go from minus J to plus J in steps of 1, passing through 0. And so this is how many there will always be. Again, hoping you have some recollection of that from your modern physics or maybe chemistry. Energy function we already know. Those are just the rotational levels. And so we sub that in. So there are 2 ways you can deal with this. And it kind of depends on whether you're at high temperature or low temperature. Low temperature, the assumption would be that there's only a few of these J values that are really going to matter at low temperature. And so you can just write out the sum. It'll have a few terms in it and just deal with it. In fact, that's a generic approach. You can always just try to do the sum. So it probably works at intermediate temperature as well. Sorry. But at high temperature, we can actually make an approximation where the J values extend to infinity and turn the sum into an integral. Let's do low temperature first. So low temperature means KBT is somehow less than that little epsilon factor. In this example, I want to say KBT is less than about 6 epsilon. Why do I say that? I say that because it then allows me to suggest that only the J equals 0 and J equals 1 level matter, right? The 6 epsilon comes from the fact that that is the energy spacing to the J equals 2 level. And so if the KBT energy scale is less than the spacing to the J equals 2, we should feel pretty confident that we can ignore that level. So let's find an expression for the probability of a molecule being in a rotational state with J equals 1. So E of J equals 1 is just 2 epsilon, as we already mentioned. Boltzmann probability is degeneracy factor, e to the minus beta energy over the partition function. So pay attention to this because you haven't seen this expression before. I'm saying here that you need to note, to make the probability behave properly, we have to include the degeneracy factor in the numerator in addition to including it in the partition function. And my claim is that you should be able to do the math to show why that is required for that to be a properly normalized Boltzmann probability in the case of degenerate levels. So this is a specific example that we're doing, but I'm also writing down for you here a very generic expression for how to work with Boltzmann probabilities when there are degeneracies present in the spectrum. So for our given conditions, we can write out the partition function as before, and plugging in only the J equals 0 and J equals 1, we get 2 terms. So we get a 1 from the J equals 0 case, so that's just e to the minus 0. And then we get 3 for the degeneracy, e to the minus 2 beta epsilon. So then plugging in for the probability, again, keep messing up. Degeneracy factor 3 appears in the numerator, e to the minus 2 beta epsilon divided by that partition function. So that's easy at low temperatures, and really, I guess you could sort of argue almost any intermediate temperature. You can just figure out what J values are relevant to you and just do the sum. But if we go to high temperatures, where let's just say kBT is much, much greater than the energy scale, I feel like that's a vague statement, but I think we'll see in the end, it's fairly easy to understand when this condition will be valid once you've worked with it a little bit. And so again, it's not like when you're thinking about high temperature, low temperature limits, the answers are not always completely rigid, but they do have to be carefully explained and assessed. But let's just go ahead and say that this is a high enough temperature limit that a lot of J values matter, right? So that you can basically go in and convert this sum to an integral. Let's say we're multiplying through by a delta J equals 1 here, but that delta J equals 1 is real small compared to the total number of J's involved. So we've got this integral, and we can now just do this integral directly by a very simple u substitution. So if we let u equal to the thing that appears in the exponential, du is just minus beta epsilon times what we see in the integrand, right? So this whole expression here is just the same as this. And so that means that the partition function can actually be written in the u substituted variable as minus 1 over beta epsilon, integral from 1 to 0. I mean, note the order here is weird, but that's because I'm actually doing the correct limits for the variable u assessed from these limits. And so that ends up being just 1 over beta epsilon, which is kBT over epsilon. So the question is, does this make sense? And there's an equipartition argument that Schroeder uses to show that it does indeed make sense. I think that you should be able to follow that type of argument and make that type of argument yourself for other physical systems. And so you want to pay attention to that. How do you use equipartition to discuss the significance and the validity of this approximate result, right? So you should be comfortable with both the math and the logical flow of that type of equilibrium argument. Sorry, equipartition argument. So just to finish up with this, let's go ahead and plug in some real numbers. So for the HCl molecule, the energy scale is 0.0013 electron volts, so 1.3 milli electron volts. So for low temperature, let's just say T is much, much less than epsilon over Kb, which is 15 Kelvin. I mean, this is interesting because it's so cold, and I feel like in a lot of circumstances, molecular system would actually condense under this. However, you can consider very dilute specimens of ultra cold molecules, and that's a pretty hot topic in physics, so I linked you an article here if you care about that kind of thing. So for high temperature, let's just say T is much greater than that energy scale, which is 15 Kelvin, and let's plug in some numbers to see when that sort of starts to make sense. So if we use the high temperature approximation, at 150 Kelvin, the rotational partition function is almost 10. So roughly speaking, that means there are about 10 relevant states in the partition function sum. I mean, that's a dangerous analysis. Remember, many, many more states could actually contribute to, could actually have a significant probability of occupation under those conditions. So it's really an intuition, but not a quantitative result. And then at 300 Kelvin, we've, yes, doubled our number of states that are involved to about 20. And so you can sort of ask yourself, oops, I messed up. You can sort of ask yourself the question, are these enough states to really justify the high temperature approximation? So in order to figure that out, I just made a little plot of the actual sum using J values from 0 up to 100 and including all the degeneracy. So I'm doing the real true sum. That's the blue curve. And then in orange, I plot the result of just assuming the high temperature approximation is valid for all temperatures. And so I plot the rotational partition function as a function of temperature, kBT in units of eV. I mark here kBT equals E, which occurs at about 15 Kelvin, so that's right about here. And so down here at low temperatures, of course, the deviation between the blue and the orange is pretty significant. You know, even at around 150, you can still visually see a clear difference. And so the question of whether Z equals 10 is good enough for you kind of depends on what precision you demand of your calculation. If you go up to about 300 Kelvin, you can still see the difference. But if you go in and actually try to measure the difference, it's less than 1%. So you can sort of start to say that around here, certainly the high temperature approximation is pretty good. So yeah, this is sort of a good way to assess, you know. So again, even at these lower temperatures where the deviation is more visually apparent, it might be that you could get away with assuming a high temperature expansion if the precision you require to analyze your physical process is not very high, right? Maybe you're trying to do an order of magnitude estimate or something. Okay, so there's an interesting question to ask, which is what is the y-intercept of the blue curve? That should be something that you could analyze real quickly and tell me about, like as an exam question maybe. I think that's all we're going to talk about today for rotation. I know this was actually kind of a long mini lesson, so maybe it's not so mini, but I should consider this as a you know, important example of how to apply the partition function. And so make sure that you go back through it and can follow through. So we'll see you in the next mini lesson.